long on acid-base titrations. So we talked about strong acid, strong base titration, but now what happens if we have a weak acid being titrated by a strong base? And once again, just to draw a little picture, right, we'd have the weak acid in our Erlenmeyer flask, and perhaps its concentration would be unknown, right? And then now we've put our strong base into the burette, and we're dripping that strong base slowly into the weak acid. So what would we see? Okay. Well, we note at our starting point here, our pH is not nearly as low as in the case of a strong acid. Okay, and that makes good sense. And then also we would see this interesting region where the pH would initially shoot up as we're adding base, but then it levels off. And so there's this region that I'm going to highlight from about here to here, and that is our buffering region. And how is it that this is making a buffering region? Well, if you think about it, if we're starting with weak acid, HA, and we add hydroxide to it, so we know that this is going to go as a full, complete reaction, okay? That's going to make A minus and H2O. But now if you think about it here in this buffering region, we haven't gotten to the equivalence point yet, right? So the hydroxide is the limiting reagent. And so that means in this buffering region, when we've added a small amount of hydroxide, but not enough to completely titrate out the HA, we have now present, let me get a different color here. We have some of the weak acid present as well as its conjugate base. And that makes a buffer. And as we know, that buffer wants to resist a change in pH. So that's why we see this initial kind of shooting up, and then it does kind of level off a little bit, but then it eventually shoots back up. So this region would represent our buffering capacity, okay? And so once we get past that region where it shoots up, we're no longer really having an effective buffer anymore. And then we hit the equivalence point, and you notice that equivalence point is not at 7.0, it's actually at a basic pH. So why is that? Well, once again, I'm going to write this reaction down, okay? So if I have now HA plus OH minus, and I have complete stoichiometric proportions of this, right? So let's suppose, suppose that I started with 1 mole and 1 mole. So we know now that those would react completely and become 0 and 0. And what I would be left with now is 1 mole of A minus and 1 mole of H2O. We don't care about the H2O. All we care about now is that I have made some of this conjugate base. And so even though I've titrated out at this equivalence point, right? All the hydroxide's gone, all the HA is gone. But now I have A minus. And you recall A minus is my conjugate base, and it is actually a pretty decent base. So this A minus, once titrated away, can now go on to react with that water and give me back more HA, which is less important. What is important, however, is that it's making hydroxide, okay? So now we've made an additional source of hydroxide. So remember, this was the hydroxide that we added, but we titrated it all away at the equivalence point. Now, once we have A minus, it goes through this weak base equilibria and generates hydroxide, which is why the equivalence point is always greater than 7.0 for a weak acid strong base. Okay.